Hello everyone, welcome back to Spectrum. Today in this video, I am going to discuss a new topic, space quantization of angular momentum. This topic is very important and it is used in most of the spectroscopic techniques as well as in determination of spectroscopic term symbols. So before making the videos on the topic spectroscopic term symbols, I thought I must have prepared this video before starting the term symbol video. So in this topic, actually, there are so many terms and they are very close to each other and little confuse the students because they do not have clarity about the terms which are used over here in the topic. So I am going to discuss in this video the magnetic dipole moment, Lama precision and Lama frequency, space quantization of angular momentum, and commutation relation of angular momentum, which is shown over here. So let's start with the video. So here I am having an electron which is orbiting about the nucleus in an orbit. Right? So it has an angular momentum which is represented by this vector L. I am just elaborating this theory over here. In one electron atom, the angular momentum L determines the magnitude of electron angular momentum. Please pay your attention. This is azimuthal quantum number or angular momentum quantum number. It determines the orbital angular momentum of the atom, right? In the hydrogen atom, an electron is revolving about the nucleus, which I have told you earlier, in a minute current loop and has a magnetic field. It thus behaves like a magnetic dipole and having a magnetic dipole. Since this moving electron is behaving like a magnetic dipole, so it has magnetic dipole moment too, right? So that magnetic dipole moment is represented by this mu L. This is our magnetic dipole moment and it is related with this relation. I am not going to prove this relation. So mu L, that is magnetic dipole moment, is equal to minus E upon 2mc into vector L. Here this minus charge, because an electron is having minus charge, therefore this term is, and because of this negative charge, this mu L is having opposite direction to this vector L. So here in this figure I have shown it. This orbital angular momentum is in this direction. So our magnetic dipole moment is opposite direction. Orbital angular momentum. And here E is the charge on the electron, m is the mass on the electron, and c is the speed of light. This small l is known as orbital angular momentum. But before moving further, I'll just bring to your notice that in some of the texts you will find small l and in some of the texts you will find capital. So what is that? So this small l represents the one electron system and this capital L represents for atom. So one electron atom like hydrogen atom, both small l and capital L are same. So here onwards I am just using this capital L because in many of the texts it is given there. Now coming to the next and important point, what is the direction? So this orbital angular moment is perpendicular to the plane of the electron orbit. Therefore, this mu L is again perpendicular to the plane of the orbit of the. So here few things which you keep in your mind is that a moving charge particle creates magnetic field, therefore it is having magnetic dipole moment. And this magnetic dipole moment is related with this orbital angular moment by this relation. And this orbital angular momentum is decided by the azimuthal quantum number. So only these are the points which are very important you need to keep in mind. Moving forward, if I just want to determine the magnitude of this mu L, then I have to put all these values. So these are known to us. Now coming to this vector L, which is the orbital angular momentum. From quantum mechanics, the magnitude of this vector L or orbital angular momentum is given by here. Small l is the angular momentum quantum number, or this is also known as azimuthal quantum number. And the important point about this azimuthal quantum number is that it describes the orbital motion of electron. And this is the h upon 2 pi, h is the Planck's constant. Or sometimes you will find cross over here, so that means upon 2 pi. On solving this equation, after putting vector L value, we will get this, and this E h upon 4 pi mc gives you Born magnetron, right? And the value of this Born magnetron is 0.928 into 10 raised to the power minus 20 ergs per cos. It is in CGS units, and 0.928 into 10 raised to the power minus 23 joules per Weber per meter. It is in MKS units. Now moving further, and here we are going to discuss about the Lama precision and Lama frequency. Since this orbiting electron behaves like a magnetic dipole, and therefore it is having magnetic dipole moment. And because of that magnetic dipole moment, when it is placed in the external magnetic field, it interacts with the external magnetic field. And so when an atom in the external magnetic field B, the electron orbit presses about the field direction as axis. E will be the axis of precision. Let the angle between B and L be theta. The orbital dipole moment, this is again having angle theta, right? Because it is just opposite to orbital angle. So it experiences a torque that is shown over here. And just because of this torque, which is perpendicular to this L or orbital angular moment, this torque causes an angular momentum to change according to tau is equal to dl upon dt. So here I'm just showing you, this is the vector L. It changes with time like this. So here is the dl. It shifts its position. dl in time dt. So what we have seen over here, changes takes place in the direction of the torque. In this torque, as it is changes, the direction of dl will changes. The change dl is perpendicular to vector L. So this is our vector L direction, and this is our dl direction. So this is perpendicular or in direction with the torque. In this way, we can say the orbital angular momentum L remains constant in magnitude, but its direction changes and it traces cone about this B or this G axis, such that the angle theta remains same between this vector B and vector L. And while it is changing its direction, that is termed as Larmor precision, means it is precessing about this G axis, and the frequency with which this change occurs, here this omega t, this omega is the angular frequency, or this is termed as Lama frequency, and this omega dt is termed as is different. Now the external magnetic field B is along G axis. The component of L parallel to the field direction is, so this is L and this is B. So if we consider the component of this vector L, so we trace a perpendicular to this, and we will get the component of this vector L or orbital angular momentum in this direction parallel to this. So that component is given by the trigonometric relationship. So Lz is equal to vector L into cos theta. So here, just to determine the value of this angle theta, we have to put the values of vector L component of this. So the values of this component and orbital angular momentum is given by quantum mechanically, and that are vector L is equal to under root L plus 1 h cross, whereas Lz component is having values ml h upon 2 pi. So here L is the angular momentum quantum number and m is the magnetic quantum number. The values of m depends on this angular momentum quantum number. Here you may have a question, why we have written only this L and Lz component? Why not Lx and Ly? Can we write that? Yes, we can write. At one time we can write L, Lz, Lx or Ly. Simultaneously we cannot write Lx, Ly, Lz, right? So the reason behind that is given by the commutation relation of this orbital angular momentum. So that is what, according to the Heisenberg uncertainty principle, only L square and its one component, either Lx, Ly or Lz, can be measured simultaneously. This fact is expressed by saying that L square commute with one of its components. That is, so here I have written L square comma Lx, and on this we are written cap, right? This is equal to L square Ly cap, L square Lz caps, and these are equal to 0. It means this L square commute with one of its component. So this cap means what? This cap suggests us that this is the operator in quantum mechanics. So that operator is written over here. You are very well aware about this Hamiltonian operator, and psi is the wave function, E is the eigenvalue. So here L square cap is behaves like an operator. So these two operators, if these are commute with each other, then they are having the same wave function and their eigenvalues are given by these relations. So L has value, here you just see L square. So L square is having value L plus 1 h cross square. If we are having the value of L, then we are doing the square root of this. So this L is having value under root L plus 1 h cross, right? And this component vector is having the value mlh cross. So these are the eigenvalues on solving this commutation relation. So I am not going into the detail of that commutation. If you are interested, then you can write me. We will do that. So here again, the next thing is that Lx and Ly are not commute with each other. So simultaneously, we cannot determine these two component vectors. Moving forward to the determination of the angle between the external magnetic field and this orbital angular momentum. Lz, its component is equal to L cos theta. So putting the values of Lz and L, we will get ml upon under root L plus 1 for this cos theta. So here these are the values. Now coming to the values of this ml. Lz is having this value. What about this ml? So ml is having 2l plus 1 value. Now you can see how these values are possible. So ml is having values from plus L to minus L including 0. You can also relate this relationship with the p orbital. So we are having plus 1, 0 and minus 1. So for p orbital we are having L is equal to 1. And here we are having plus 1, 0 and minus plus L to minus L including 0. This many values for ml are possible, and on adding all such values we will get 2l plus 1 value, this ml, right? So in this manner, if ML is having this many discrete values, therefore theta will also have this many values corresponding to this relationship. So here what I have written is that the angular momentum vector, vector L, can have 12 plus 1 discrete orientation with respect to the external magnetic field. This quantization in space is known as space quantization. So I am just showing another example. So here we are just elaborating this example for L is equal to 2, means for d orbital. So here this L is equal to under root L plus 1 h cross, and on putting the value of L we are getting under root 6 for this. This is the magnitude. The direction of angular momentum is pointed in certain directions depending on the L and M value. So now we are just measuring the number of thetas which are possible for this system as it is quantized. So here for this L is equal to 2, ML is having 5 different orientations, and corresponding to these 5 different plus L including 0 to minus L. So plus 2 to minus 2 including 0, plus 2 plus 1 0 minus 1 minus are the values for this ML. Now coming to the Lz is equal to ML H cross. So putting all these values, Lz, this component vector is having a 2L plus 1 value, and corresponding to this we are having plus 2 H cross, plus 1 H cross, 0 minus 1 H cross, minus 2 H cross. And here this is the magnitude, and magnitude will remain same for all these components, but their direction, orientations are the direction or orientation. I am showing this with this figure. So here what you have seen, we are having 5 Lz for this L, right? So 5 component vectors are there. So these are making this component. This is the component. So here you are having 2H cross, 1H cross, 0H cross, minus 1H cross, minus 2H cross. All these Lz components have drawn over here. But all the component vectors having the same value of L, you can see here, right? And corresponding to M, L is equal to plus 2, we are having this maximum component, right? What I have shown earlier, the Lama precision and Lama frequency. So here this component vector, this L vector forms a cone about this G. All these will form same kind of cones about this G. In this manner, this 2H cross forms an angle 35 degrees. So theta for each of the component vector is 35 degrees, 6 degree, 90 degree, 114 degree, 145 degree. The important point is that it cannot have 0 and 180 value, means the L cannot be, or the orbital angular moment cannot aligned exactly parallel or anti-parallel to B, because this ML is always less than under root L plus 1. Therefore, we are having values. Now the important points which am going to summarize here. These regions of space are called orbitals. For L is equal to 2, which is known as d orbital. The orientation with maximum positive value of ML will have maximum magnetic field component parallel to the direction of magnetic field. Such an orientation of orbital angular momentum will therefore be of lowest energy. Corresponding to ML is equal to plus 2, we are having maximum component vector in the parallel direction, and this is having the lowest value. Similarly, this negative value of maximum component vector in anti-parallel direction B, and it is of highest, and rest are in between, right? In the absence of external magnetic field, all the orientations of the orbital angular momentum have equal probability. So these orientations have equal probability in the absence of applied external magnet. It can be understood by this. A spectral line obtained in the absence of external magnetic field due to shift of electrons from higher to lower d orbit. That will split into 5 lines in the presence of external magnetic field. So these are the important points which I thought are important to know about the orbital angular momentum. And three things are important. One is orbital angular momentum, second one is magnetic moment, and the third one is space quantization of orbital angular momentum, which suggests us the same magnitude of the component vectors but different directions or different orientation. So I hope guys you understand the concept which I have discussed here in this video. If you find this concept helpful and interesting also, so please subscribe my channel, give me a thumbs up, share this video with. Thank you. Thanks for watching.